Welcome to the 10th lecture of my series on thermodynamics. In the last lecture, we had met a very important entity, the heat engine. This is important not only because of its practical importance in the Industrial Revolution and subsequent evolution of human civilization, it's also very important as a tool towards understanding the basics of thermodynamics. This will be clearer as we proceed with these lectures. Let me briefly remind you that the most general heat engine was something which went in a cyclic process, as signified by this closed curve drawn here, which interacts with a bunch of reservoirs at temperatures T1, T2, Tn, etc. and taking in heats Q1, Q2, Q3, Qn, etc. from each one of them, and using all of this to do work W. And according to the first law, since delta U for the system is 0, the system undergoing a cyclic process, capital Q, the sum of all the Qi's must be W. We also defined Q plus and Q minus. Q plus was a sum of all of the Qj's which were positive, and Q minus was a sum of all of the Qk's which were negative. It's obvious that Q, the total heat gained through all the reservoirs, is actually a sum of Q plus and Q minus. And efficiency of the heat engine, eta, defined as the amount of work you get per unit heat supplied, W by Q plus, is easily seen to be, according to this, 1 plus Q minus by Q plus. In the last lecture, we also talked about the simplest heat engines. We saw that one which has no reservoir at all is completely trivial. It doesn't interact, does nothing. The next simplest choices, which had one reservoir and one place to do work, or two reservoirs with no need for doing work, respectively, these two engines would have been very useful had they existed. But we have already said in the last lecture that it turns out, after a lot of experimentation, the useful forms of those two engines don't exist. You can have an engine which converts work into heat 100% efficiently. There is none which can convert heat with 100% efficiency while going in a cyclic process. Similarly, you can have an engine which transfers a heat amount from a hot body to a cold body without any intervening work. That actually doesn't even require an engine. That's something that will happen spontaneously when you put two bodies in thermal contact with each other. However, it's reverse. An engine which can actually carry heat from a cold body to a hot body without any work input cannot exist. We had not explained why they can't exist. In fact, frankly, within thermodynamics, we can't really explain these things. We can only claim that this is a result of lots and lots of experiments, essentially the result which is called the second law of thermodynamics. But once again, we are going too far ahead of ourselves. We had decided that the most simple, non-trivial engine that we can have, one which will actually exist and do work for us, is a system which undergoes a cyclic process. Of course, every engine has to have a system which undergoes a cyclic process, while exchanging heat with two reservoirs, the bare minimum that you can have, and carrying out work on one or more external objects. As I said in the last lecture, the work which a heat engine does can be spread out over many objects. However, the identity of these objects is really not a concern as far as thermodynamics is concerned. These could be very important in the mechanical aspects of the engine. But as far as thermodynamics is concerned, it doesn't really matter what it is that gets work done upon it. So we will lump all these possible avenues for doing work into a single work arrow, whenever we draw a diagram of a heat engine. So the simplest non-trivial engine simply is one which has two reservoirs with two heat arrows going in and one work arrow going out. As we said at the end of the last lecture, a special case of such an engine is what is known as a Carnot cycle, something which has a place of immense importance in both the history and the theory behind thermodynamics. So let us now take a look at the Carnot cycle and try to calculate its efficiency for some simple working substances. The Carnot cycle is really a very simple cyclic process. It's composed of 4 steps between states which we will call A, B, C and D. The step from A to B is an isothermal expansion at temperature T1. This temperature is a special kind of empirical temperature which is the ideal gas scale temperature. At least we are going to use the ideal gas scale temperature unless otherwise mentioned. However, as far as the theory is concerned, it doesn't really matter if we had used some other temperature. But the calculation that we are going to do will give us a specially simple result if we use the ideal gas temperature scale. We will see later that that is not really an accident. Moving on, the second step, the step from state B to state C, is an adiabatic expansion till the temperature reaches a smaller value of T2. From C to D, an isothermal compression at temperature T2. So D reaches back to a much smaller volume than C. But as you will see, typically for an ideal gas Carnot cycle, a volume which is still larger than the initial volume, the volume at A. Final step, from D to A, this completes the cycle, is an adiabatic compression back to the initial state. Now, all of these states in the Carnot cycle are quasi-statically carried out. Now, what makes Carnot cycle extremely important is the fact that I am stating ahead of its time in the sequence of lectures. I've already said that in the last lecture. The Carnot cycle is actually the only reversible cycle that can run between two reservoirs. This is what makes the Carnot cycle really so special. But this is something we are going to only fully appreciate after we learn about reversibility in a future lecture. Now, let us directly calculate explicitly the efficiency of the Carnot cycle with some special choice of a working substance. The first calculation that I am going to do is one involving the ideal gas. Let me remind you that this is a gas which not only obeys PV equal to nRT, the standard ideal gas equation of state, it also obeys along with it a special version of Joule's law. Joule's experimental finding was that for an ideal gas, the internal energy depends only on the temperature and not on the volume. What I am calling an ideal gas is one in which this dependence is very special. U of T is linearly proportional to T, which essentially means that its heat capacity at constant volume, Cv, is a constant. Now, for such a gas, if we carry out these 4 steps in sequence, we can easily figure out the following. In the first step, P1 V1 to P2 V2. Let's show you the picture here. This is pressure along this axis and volume along this axis. And the gas is expanding from P1 V1 to P2 V2 isothermally. So this is, according to the ideal gas equation of state, a PV equal to constant curve. Remember, because this process is quasistatic, at every stage of the process, the system is infinitesimally close to equilibrium. So we can actually draw a solid line from P1 V1 to P2 V2 Because what we are saying is that even at the intermediate stages of this process, the system is almost perfectly described by a point on the PV diagram, an equilibrium state. Now, for this isothermal expansion, we can easily calculate how much Q plus is. Remember, U depends only on temperature for an ideal gas. In particular, for the special kind we are taking, it's just proportional to the temperature. Here, the expansion is isothermal, so there is no change in internal energy. Delta U is 0. As a result, Q plus, the heat which goes in here, is actually equal to W. Note that we can easily identify the heat going in here as Q plus and the heat going out as Q minus, simply because these are the only two places where heat exchange can take place. And during an isothermal expansion, the gas requires heat from the outside in order to be able to do work against external pressure. During the isothermal compression, it's the external pressure which does work on the gas, so the gas does negative work. And once again, the heat exchange during this process is exactly the same as the work done during this process, which is negative, and that's Q minus. Moving on with the calculation, Q plus is the integral, of course, in this case of P dV. This, of course, is nothing but W, but as we have just seen, Q plus is the same as W. And in order to carry out this calculation, we need to get rid of P in favor of V. And it's easy to do that. From the ideal gas equation of state, we get nRT1 by V dV. And the integration now is absolutely trivial because T1, remember, is a constant. Isothermal process after all. And the integral simply becomes nRT1 log of V2 by V1. Now the other isothermal process, the isothermal compression, which leads to this Q minus, we don't really need to calculate the Q minus all over again for that. You can just use the same expression as the one we have derived here, except that the temperature T1 has to be replaced by T2 and the final and initial volumes during the process, V2 and V1, have to be replaced by the final and the initial volumes during this process. So this has a log of V4 by V3. Before moving any further, let me point out that V2 here is obviously more than V1. It's an isothermal expansion which takes you from here to here. So log of V2 by V1 is log of a number which is more than 1. Hence this is positive. On the other hand, Q minus is basically an expression which has log of V4 by V3. V4 is smaller than V3, log of a number less than 1. So this is negative. So our identification of this as Q plus and this as Q minus was perfectly alright. Now that we have Q plus and Q minus, and note that these are the only two heat terms that we need to calculate, there being no other heat exchanges here because it's adiabatic, or here because it too is adiabatic, what we end up with is an efficiency given by 1 plus Q minus by Q plus, which is simply 1 plus T2 by T1 into log of V4 by V3 by log of V2 by V1. Now this looks like a reasonably simple expression, but still not a very simple expression. But note that we have not made use of the other two paths as yet. The fact that these two paths are actually adiabatic, this is an adiabatic expansion and this is an adiabatic compression, is something we have not actually used so far. Now how do we make use of that? In an earlier lecture, we had shown that for an ideal gas, adiabatic processes obey a very simple constraint. In particular, the constraint it obeys is T times V to the power gamma minus 1 is a constant for an adiabatic process. Here gamma is simply Cp by Cv. This formula should be pretty familiar to all of you, even from high school physics. And we had actually derived this explicitly in a previous lecture. The one thing that you have to remember about this derivation is that this works only if gamma, the Cp by Cv ratio, is a constant. which is true for the ideal gas, where Cv is a constant and Cp, which is Cv plus Nr, is obviously another constant. Now, because at this case, the temperature here is T1 and the temperature here is T2, we have T1 into V2 to the power gamma minus 1 is T2 into V3 to the power gamma minus 1. On the other hand, as far as this is concerned, the initial temperature is T2. The final one for this process is T1. So you get T2 V4 to the power gamma minus 1 equals T1 V1 to the power gamma minus 1. So quite clearly, if I divide this through, you get T1 by T2 is V3 by V2 to the power gamma minus 1. On the other hand, on this side, I get V4 by V1 to the power gamma minus 1. Now, since these two numbers raised to the power gamma minus 1 are equal to each other, they must be equal to themselves. So, V3 by V2 has to be equal to V4 by V1. Now, why is that important? Because it gives us a relationship between these two logarithms. Note here you have V4 by V3 and here you have V2 by V1. Basically the two expansion ratios. From the formula that we have just derived, it's very easy to see that V4 divided by V3 is the same as V1 by V2. So log of V4 by V3 is of course log of V1 by V2, but that means it's negative of log of V2 by V1. Now go back to the expression that we have just derived. Eta is 1 plus T2 by T1 times this ratio of logarithms, and what we have just proven is that this ratio of logarithms is minus 1. So at least for the ideal gas Carnot engine, the efficiency is given by eta equals 1 minus T2 by T1. A very, very simple function which depends only on the two reservoirs or only on the temperatures at which the isothermal compression and the isothermal expansion is being carried out. For our next example, we change the working substance slightly. It's still an ideal gas, but what we are calling a generic ideal gas. Here, PV of course is equal to nRT, but in addition, U could be any arbitrary function of temperature. Now, under such a condition, Q plus and Q minus calculations will go along the same way as before. Both, after all, really were equal to the corresponding works done, which was because U did not change as temperature did not change. And remember, the amount of work done in an isothermal process depended only on the PV equal to nRT equation, so that will still be the same. And at this stage, you are left with eta equals 1 plus T2 by T1 log of V4 by V3 divided by log of V2 by V1 as before. However, the important question here is about the adiabats. Note that Tv to the power gamma minus 1 equal to constant. The equation that we had used for an adiabat is actually valid only if Cv is a constant. If U is some arbitrary function of T, then Cv would not be a constant. So let us take a look at that properly. So let us consider the equation for an adiabat, at least in terms of temperature and volume, for a quasistatic adiabat in the case of a generic ideal gas. Starting from an initial state with temperature Ti, volume Vi, to a state temperature Tf, volume Vf. So D cross Q, as always, is du plus Pdv, and du in this case is just heat capacity C of Tt. This is really Cv, but doesn't really matter as far as our calculation is concerned. And Pdv is, of course, nRT by V dv. For an adiabat, D cross Q is 0. So this is the equation that we have to solve, that this differential equals 0. Now this equation is actually very, very simple to solve, as we have already seen before. You just divide through by capital T or nr times capital T and you end up with C of t by nr dt by t plus dv by v equals 0. Now, if we integrate this equation, we are going to get 0. From the right hand side, remember this is a definite integral that we are doing from this state to this state. So the right hand side, of course, will integrate to 0. On the left hand side, this integral is something we cannot really evaluate unless we know exactly what C of t is. But in principle, the moment you know C of t, this is an integral that you can carry out. Of course, here we only have the limits of t, ti and tf simply because v doesn't even appear anywhere in this integrand. On the other hand, dv by v integrates, of course, to log of vf by vi. Now let us use this equation for the two adiabats we have. T1 V2 to T2 V3. This is one adiabat. Here the final volume is V3, initial volume is V2. So this term simply becomes log of V3 by V2 plus 1 by nr. The initial temperature is T1 for this process, final temperature is T2. And this integral is what you have. Once again, an explicit formula that can be obtained here only if we know C of t. However, as we will soon see, we don't really need to know that. The fourth step of our process, the other adiabat, goes from T2 V4 back to T1 V1. And for that, the same equation becomes log of V1 by V4 plus 1 by nr. Now the integral goes from T2 to T1 of C of t dt by t, and this whole sum is of course again equal to 0. But the important thing here is these two integrals are essentially the same integral with just their limits switched. So when you add these two together, irrespective of whatever C of t is, they will just cancel each other out. So adding this equation with this one immediately gives me log of V3 by V2 plus log of V1 by V4 is 0, which essentially means V3 V1 by V2 V4 is 1. And that gives me the same result as we had before. Log of V4 by V3 is minus log of V2 by V1. And so the efficiency eta, which is given by this, simplifies to the same expression as before, 1 minus T2 by T1. So we have seen that both for an ideal gas, an ideal gas with constant heat capacity, and a generic ideal gas, something for which U could be an arbitrary function of temperature, the efficiency is ultimately given by the same expression. Eta equals 1 minus T2 by T1. Let me once again remind you that the temperatures used here are empirical temperatures, but not just any empirical temperature. These are temperatures according to the ideal gas scale. As our final example, at least in today's lecture, we are going to work out the efficiency of yet another Carnot cycle. This time a Carnot cycle which uses as its working substance a real gas, a gas which obeys the van der Waals equation of state. Now, as you are all aware, the van der Waals equation of state looks like a slightly deformed version of the ideal gas equation of state. Instead of PV equal to nRT, you have P plus n square A by V square into capital V minus NB equals nRT. And in addition to this, we need to know how the ideal gas's internal energy changes with temperature and volume. Unlike the case of an ideal gas where the U depended only on temperature, at least U per unit mole, U by N depended only on temperature, you have to have volume dependence here as well. This is sort of easy to understand from the microscopic picture which we use to quote-unquote derive the van der Waals equation. There, let me remind you, the term n squared A by V square basically takes into account the fact that the molecules tend to attract each other, at least for a positive A. And so, when a molecule gets very close to the bounding surface of the volume which encloses this gas, it feels an attraction from only one of its sides because there are no molecules on the other side, there's only the wall, and hence gets slowed down and can deliver only a smaller impact on the walls compared to what an ideal gas molecule would have done. So the pressure becomes smaller than the effective ideal gas pressure, which is corrected by putting in P plus n square A by V square. While we are saying this, let me also remind you that this term essentially comes from the fact that the molecules are not really point molecules, they occupy some space. Of course, the total volume of the molecules is proportional to the number of moles, and this NB term essentially tells you that out of the total volume capital V, this NB is occupied by the molecules themselves, so it's taken out from the actual space where the molecules can move. Now, because the molecules attract each other, it's easy to understand why the internal energy changes when the volume increases. When the volume increases, these molecules have to move further apart, and in order to move apart, they have to actually do positive work against each other, thus raising the internal energy. Note that minus n square A by V term is actually a term which increases as the volume goes up. 1 by V decreases, but because of the minus sign, this actually goes up. Now, as far as thermodynamics is concerned, these microscopic ideas are not really important. What is important is that you do have an equation of state and you have at your disposal a function of temperature and volume which represents the internal energy. Using this and only this information, we can calculate the efficiency of a Carnot cycle using a van der Waals gas. The calculation will be slightly different this time. For example, in order to understand the heat absorbed as well as the adiabats, it's actually easier if you work out d cross q in the general case first. D cross q, of course, is du plus pdv. du is given by n times f prime t from this expression, dt, plus n square A by V square dV. And to that, of course, you add the pdv term from the work. And when you combine all terms together, you get n f prime t dt plus p plus n square A by V square dV. Now, using this general expression for d cross q, the heat absorbed, let us consider first the isothermal expansion from P1V1 to P2V2. Here, of course, temperature is a constant, so dt is 0, and this term drops off. You just have this. And temperature, of course, is constant at T1. So d cross q takes the form P plus n square A by V square dV, and according to the van der Waals equation of state, this is simply nR T1 by V minus NB times dV. So Q plus, the heat absorbed, not the work done in this case, but the heat absorbed, is simply nR T1 with integral of dV by V minus NB from V1 to V2, that is log of V2 minus NB by V1 minus NB. Now the other isothermal from P3V3 to P4V4 plays out very similarly. You can immediately calculate Q minus simply by substituting the corresponding terms. Instead of T1, you have to put in T2. Instead of V2, the final volume here, you have to put in V4. Instead of V1, the initial volume, you have to put in V3. So now, once again, we have a rather complicated looking expression for the efficiency. Eta works out to be 1 plus Q minus by Q plus, that is 1 plus T2 by T1. This rather horrible ratio of 2 logs sitting here. Of course, this is very similar to the ideal gas expression in a way, and to check that this is still on the right track, we can try taking the limit as b goes to 0. When you do that, you do get log of V4 by V3 by log of V2 by V1. Now, how do we simplify this ratio? For that, we use the same trick that we had used for the ideal gas. These two steps, the second and the fourth, from P2V2 to P3V3, this goes from T1 to T2 temperature, and this goes from T2 to T1. These are adiabats. And so for them, D cross Q is 0. Now note that in general, you can always replace P plus N square A by V square using the van der Waals equation of state by this expression, nRT by V minus NB. So this is what the equation looks like. You have only T here, but here you have a mix of T and V. But that's easily remedied. All you have to do is divide by nRT and you end up with F prime T, this derivative, by R times dt by T plus dV by V minus NB is 0. Now if you integrate this from this state to this state, which is from temperature T1 volume V2 to temperature T2 volume V3, this expression simply gives you F prime T dt by T into 1 by R integrated from T1 to T2 plus V2 to V3 integral of dV by V minus NB equals 0. And now this simply gives me that for the path 2, you get this integral plus log of V3 minus NB by V2 minus NB equals 0. Once again, as in the case of the generic ideal gas, I cannot really completely solve for this unless I know the form f of t and hence its derivative. However, I don't need to, as we have already seen before. 2 is an adiabat, so is 4, actually not 3. The last step of my Carnot cycle. And for that, the initial temperature is T2, that's the temperature at which the adiabat starts, and the final temperature is T1. The initial volume is V4, the final is V1, and so we can immediately write down the adiabat just by changing these tiny details. And once again, whether I know f prime t or not does not matter. These two integrals will always add up to 0 because they are the same integrand integrated over switched limits. So immediately we get these two things added together gives you 0. That is, this particular product here is 1. And that, with a small bit of manipulation, immediately tells you that V4 minus NB by V3 minus NB equals V1 minus NB by V2 minus NB. And that, if you plug that back in the expression for the efficiency they have found out, tells you that these two will cancel each other with a minus sign, and you once again get the same efficiency back. Eta equals 1 minus T2 by T1. By the way, this temperature is again the ideal gas temperature. The van der Waals equation of state, as it is stated, has nRT on the right, but the T is the temperature according to the ideal gas scale. So we see that in each of our 3 calculations, where we carried out an explicit calculation for the efficiency of a Carnot cycle using different working substances, we ended up with the same result. Of course, this fact cannot be an accident. The fact that all of these 3 examples led to the same efficiency points to something deeper. And that something deeper is the second law of thermodynamics. Something which we will start discussing from the next lecture. But before we end this lecture, let me confess that I have actually cheated a bit. The expressions for the internal energy that we have considered so far, the fact that the internal energy for the ideal gas is only temperature dependent, was something which we found from Joule's experiment. So we can say that at least is on strong experimental footing. The expression that I have given you for U of T and V for a van der Waals gas had this volume dependence of minus n square A by V. That actually is the volume dependence that's predicted by the second law. So it's not a surprise that this efficiency value, which as we will see later is a consequence of the second law, actually follows even when we are using the van der Waals gas. You can try this at home. Instead of assuming U of T, V for a van der Waals gas is n f of T minus n square A by V, just assume that it's a function of temperature alone. Perhaps even as simple as 3 by 2 nRT. Then try to calculate the efficiency of the Carnot cycle with such a gas. That calculation, despite the simpler form of U of t, is actually going to end up being more complicated. But more importantly, you will not get this 1 minus T2 by T1 result. And the reason behind that is simple. The expression for van der Waals gas's energy that I have just stated, that U of t is a function of temperature alone, is actually inconsistent with the second law of thermodynamics. As I have said over and over again, this is something which we can only truly justify once we have studied the second law. This is a study which we are going to embark on from the next lecture, starting with a thorough understanding of what the notion of reversibility really means. Till then, goodbye.